So my name is Krzysztof, I came from Poland. And first I would like to thank you for having me on this outstanding conference in a pub. So my talk is going to be about recursion schemes. And the title is Recursion Schemes by Example. And the examples I chose are going to be, I believe, quite simple and trivial because the next talk by Dominic is going to show you some real-world applications of recursion schemes in the wild. So this talk will be, I believe, a kind of an overview of recursion schemes. So first, before we start speaking about recursion schemes, let's take a look at recursive data structures. So we have recursive data structures all around, right? JSON is a recursive data structure. It can contain an inner JSON, which can contain an inner JSON. So we can often view recursive data structures as trees. Lists are also recursive data structures, obviously. A list is either an IL or a cons, which consists of an element, data, and an inner list. So it's also recursive. Free monads are recursive data structures. Now this is a less obvious example. So a free monad is often used to represent a description of a program. So in fact, a free monad is some data or some inner deeper structure, which can be data or deeper structure represented by a DSL. Okay, so what we can do with recursive data? We can process it in different ways. We can render it just to print our recursive data in some way. So for example, we have a JSON object which we would like to represent as a string. So this is a tree which we would like to somehow collapse into a single value of a string. We can transform recursive structures in other kinds of structures. So this is more sophisticated usage. For example, on the left we have an Avro schema. On the right we have some SQL schema. And there is a great talk by Valentine cases. The link is available in the slides. The slides will be published after the talk. And it's a whole talk about a real-world application of recursion schemes in a project where there were many schemas of different types, Avro, Parquet, and others, and they used recursion schemes to transform schemas. So I highly recommend this talk. We can optimize data structures. So we have a recursive expression. It's an arithmetic expression, sum of int value of 5 and a multiplication, which is a deeper nested structure of 2 int values of 8. And we can use recursion schemes to transform, to optimize this and represent the multiplication as a square, for example. And the simplest examples of recursion schemes are starting with generalized folds. What does this mean? This means that if we have a tree, our recursive structure, we want to traverse it somehow to build a single value out of it. Right? So we have the leaves of the tree, which we would like to fold bottom up using some transformation functions and build new data, proceed recursively until we get the last value. For example, the string built out of a JSON. So this is folding bottom up, but sometimes we also would like to unfold top down. So to build recursive data, to grow a tree from a seed, so to speak, starting from a single value and using some function and recursively grow a tree out of it. But recursive schemes are tools that allow us to do this in a very elegant way by focusing on separation of concerns. So I remember from school and from university that often recursion was defined on the blackboard in a similar way to this example, that there is a recipe for transformation, and it concerns only a single node of a recursive structure. So for example, we have this arithmetic expression built out of smaller expressions like sum, multiply, square. And the definition of the transformation is a recipe only for a single layer. So we can say that if you want to render such an expression into a string, then if it's a sum of two expressions, then let's print it as a plus b. If it's a multiplication, then print it as a times b. So this is what we're aiming for in our code, such a way to represent recursion transformation without explicitly using recursion here, because the text function is not called, it's not written anywhere else. So one thing is the definition of how to process a single node. Another thing is the traversal itself. So we need some kind of recipe for the transformation, for the traversal. So we can say, I want to fold my tree bottom up using this recipe. Or maybe I would like to unfold top down. So once we have a recipe, once we have the scheme, which is the recursion scheme, the fold bottom up command, and our recursive data, and we put it all together, the magic happens, and we get our result. And what I would like to show you today are some tools to avoid writing this middle part, the scheme itself, because it's something that can be generalized, extracted, and available as a library. So here's an example of folding bottom up. We have our DSL, which is a SQL expression, let's say. A few examples extracted, maybe string concatenation, average, count, negation. And the ideal code that we are aiming for is something like below. So this is just a pattern matching against a single node. So if the node is an average, print it as an AVG of expression. And this E1, E2, or E are just strings. So that's what the ideal code that we would like to have without using recursion explicitly. There is no recursion here. There's just a recipe for processing a single layer. And in recursion schemes, this kind of recipe is called algebra. This simple version is called an algebra. So algebra is simply a function from a node to a string, in this case, to a T. If we wanted to write similar code using manual recursion, we would end up with code like this example. So the recursion now becomes explicit. The code is hard to read, but the problems with that code are not only aesthetic, but it's also not tail recursive. It's difficult to maintain. It's not composable. So when you start working with recursive data and you run into problems with code similar to this one, that may be a sign that you are going to need recursion schemes to represent your transformation in a more elegant way. And that's where Matryoshka comes in. So Matryoshka is an open source library maintained by the type level group. The word Matryoshka means a Russian doll. It's quite of an iconic thing, a doll that contains smaller dolls inside. So that's, I believe, a great metaphor, a great name for a library for recursion schemes. It's a Scala library based on Scala Z. I believe I heard about something called Matryoshka for cats, and I'm not sure if it's an actual library. So the algebra that we saw, the recipe for transforming a single node, can be used on a structure using something that Matryoshka provides as called a catamorphism. So catamorphism is the whole scheme of processing a recursive structure bottom up with this folding technique. So we don't have to worry about writing the algorithm about how to do the whole loop or the whole recursion ourselves. We can get we can take the expression, a SQL expression built out of smaller expressions, a recursive expression, and just call .kata and provide an algebra recipe for a single node. And then the magic will happen, and the result will be just a string in this case. So kata here is provided by Matryoshka. It's a syntax utility, but it's just a function that can take your expression and an algebra and do all the recursion for you. This way we keep the separation of concerns. Matryoshka is concerned about doing the traversal, the recursion. We are concerned about defining a pure way of working on a single node. There is also another morphism. There are a lot of morphisms actually in Matryoshka. I will cover a few of them, the most interesting ones that I found and usable in our projects. So anamorphism is a recursion scheme for doing the traversal top-down, so for unfolding data. Let's say in this trivial example we have a number and we would like to represent it as some kind of binary way, so we can decompose it in different steps into sums or multiplications, so the whole thing becomes a multiplication of sum multiplied by sum, and etc. And in Matryoshka, again, we define an algebra. This time it's called co-algebra because it's a counterpart to normal algebra used by catamorphism. So it's called co-algebra because it's a function going the other way, from a value to a node. So in this case, if we have a value, integer value 0, we build a node int value of 0, etc. If we have a not 0, not 1, not 2, but some other value, if it's divisible by 2, then it will build a multiply node. And with this flat definition, we call Ana on our number, on the value itself, on the initial value, and we apply this co-algebra, and Matryoshka would build the whole structure for us. Now, one thing that you can notice here that may be unknown to you is the fixed type. So many presentations on recursion schemes start with a detailed description of what is the fixed type, and I wanted to take a quite different approach. So for now, let's just think of the fixed type as a wrapper that's required. It's a type provided by Matryoshka. And let's think of it as a wrapper provided for you to be able to make the magic work, okay? So we have to use the fixed type in some cases, and yeah. Catamorphism. Sometimes we have our transformation of a single node that doesn't produce just a value, but a wrapped value. We are functional programmers after all, so we have a lot of monads and other wrappers. Usually we deal with effects. So quite often the recipe for a single node produces a value with some context. In this example, we have query rendering to string where something can go wrong, so we would like to represent this in a type-safe way with either. So parsing of a single node can produce not only a string, but maybe also instead an error. So we wrap it in either, but we can't use just normal catamorphism here, because when we fold nodes bottom up, we get two eithers, and we have to somehow flat map them, or actually use the applicative apply function to merge two eithers together in this operation. So we don't have to worry about it. We just use the different flavor of catamorphism, which is called kata M, and it takes a different kind of algebra, which is algebra M. And algebra M is capable of handling monads for us. So again, we have our expression. We call kata M on this expression, providing the algebra. And the result will be just a single final either in this case. Another interesting morphism is paramorphism, which can be viewed as an enhanced catamorphism. So in case of catamorphism, this first example shows just normal catamorphism. What we deal with is a single node and values which come from the transformation of the previous nodes. So when we process a node, we get an input. Here there are two strings, E1 str, E2 str. Two strings that are results of processing of the lower nodes in the previous step of catamorphism. So these are strings, two strings. We work with two strings. So we can just put them together into the final string. But sometimes the strings are not enough. Sometimes we would like to know where do these strings come from? What was the initial structure that made these strings possible? So for such cases, we can use paramorphism. So it uses once again, a different kind of algebra called G-algebra. And we can see that this concatenation pattern matching here doesn't work on two strings, but on two tuples. So each tuple represents now a string, and also additionally a bonus, which is a source structure, the structure that was used to produce that string. And based on that, we can maybe do some more sophisticated processing. For example, some conditions. Another cool thing that we can do with recursion schemes is tagging of nodes. So this can be used, for example, if our recursive structure represents an expression of some language. At Software Mill, we used recursion schemes to transform queries from some kind of a general language into PostgreSQL language, SQL queries. So working with languages is a common case for recursion schemes. And in expressions in some language, sometimes you may need types. So you can write your own typer using recursion schemes. For example, if you have a simple arithmetic expression, and we have two possible types, integer and decimal. So adding two integers is an integer, but adding an integer to a decimal, let's say that the result type would be a decimal. So what we would like to do is not to actually fold the structure into a single final value, but just add some extra information. Just put some additional data on the nodes and make it tagged with types. So there is a recursion scheme allowing you to walk through the tree and add some extra information. And this is where Cofree comes in. So Cofree is a comonad to a free monad, but again, I believe this is out of scope here. We can just think that Cofree is like a container with some nested data and a value. And in this case, the value can be our type. So each of the nodes in our tree from just an expression becomes like a pair of expression and type. And this pair is wrapped in the Cofree type, which gives us some nice capabilities. So we have an algebra transforming an expression, just an expression, into a Cofree of expression and type. And again, it's just a flat recipe for transformation, saying that if it's a sum of two values, okay, so here we are missing a condition, obviously. So if there should be a condition. If these two values are integers, then this will be Cofree of integer, otherwise decimal. And then we can get our expression, call catamorphism on it, and provide this kind of algebra. And this kind of algebra will not collapse the thing into a result value, but it will produce a Cofree of expression tagged with an additional type. And then we can run kata again on the Cofree, because Cofree is a special type that supports catamorphism. For example, with rendering to string to display the types. So we have an expression, we run catamorphism twice with two different algebras. It composes really nicely, and it keeps the separation of concerns in two different places. recursion schemes are more than folds. There is also something called transkata T, which allows you to modify certain nodes of the tree selectively. So you can write a function from a node to a node, from expression to expression. And for example, optimize if it's a multiplication and all the two arguments are the same, transform it into square. So the tree will remain the tree of the same type, but some nodes can be transformed in this very simple way. So we just define such function and run transkata on an expression providing this function, and the traversal and replacement will be done for us. With manual recursion, such a thing would be much more difficult to handle. So this is where we come to type classes. Matryoshka provides many type classes, but these three are crucial. It's recursive, co-recursive, and b-recursive, which is recursive plus co-recursive. And you can always write an instance of this type class for your type, but you can also use some predefined types like fix, mu, new, list, the mentioned Cofree and free, which already have instances of these classes, type classes. So once you have an instance of recursive or bi-recursive for your type, you can use all the recursion schemes on them. So if you want to run kata on your expression, transkata, anamorphism, any kind of morphisms, all you need is a recursive instance for your type. And if you wrap your type in fix, which is already provided by Matryoshka, you will have the instance. That's why we could run catamorphism on Cofree, because Cofree has an instance of bi-recursive. Now, back to free monads. As we said, free monad is a description, maybe used as a description of a program, because there are other applications. And somewhere in Matryoshka, there is an instance of b-recursive for free. And but you don't have to use this. Actually, free monads come with catamorphism already, because free monads can be interpreted, can be fold mapped with an interpreter, a natural transformation. And once you look into sources of Scala Z of a free monad, you will see that the fold map function has a Scala doc, which says that the fold map is a catamorphism. So at this point, I felt like the apprentice got enlightened, and this got me appreciate recursion schemes even more as something that exists. It's kind of knowledge that you don't invent but discover. So another elegant thing in functional programming where things come together. So free monads, if you use free monads, you've been doing catamorphism when you're fold mapping them, but you didn't know probably. And as I mentioned, that's just the tip of the iceberg. So I ran a training on recursion schemes for 8 hours in April, and this was also at the tip of the iceberg. But all the materials from the training are available on my GitHub account, and there is a lot of text, a lot of explanation, examples, exercises, so you can go deeper and deeper and check recursion schemes for yourself. And also, I believe that the next talk will show you some really cool real-world applications. And that would be all. Thank you.